Hello, my name is Tim Matson. I work at Intel in the what do they call microprocessor and programming research lab. I've basically spent the bulk of my career trying to make parallel programming as usable as possible by application programmers. I often like to introduce myself by pointing out that I am not a computer scientist, and I'm very proud of that fact. And what I mean by that is not to jab computer scientists. Well, okay, yeah, to jab computer scientists, but also to emphasize that I really think computer science, if you just look at it in isolation, at least for me, it's kind of boring. To me, it's all about what you can use with it. So my background is in theoretical chemistry, and so for me, a computer's always been a tool. So I'm very, very pragmatic. I appreciate the work of architects, and I definitely appreciate compiler writers, because I could never write one myself. But it's really all about making computing and making computers usable. And because of that, I've been dragged kicking and screaming into a number of parallel language projects. And one of them is OpenMP. I'm one of the original core of people who created OpenMP. I'm also one of the original core of people who created OpenCL. I also was involved on the ground floor with HPF and with MPI and with some Parlog dialects. So I've been all over the map in parallel programming languages. So let's start talking about OpenMP. It's not my laptop, so I have to figure out. But I've learned my lesson over the years that this is probably the single most important slide I'm going to show you is a disclaimer. All right. These are my views. They're not the views of Intel. What this means is I did not send these slides to an Intel lawyer to go over and make sure that they're correct and safe. So if you see anything bad, like if I violate a trademark or I use someone's name in the wrong way, please don't get mad, or get mad at me, not Intel. The other thing I want to emphasize, even though it's not written on this disclaimer, is I'm in a research lab. I pretty much know nothing about any Intel products that you couldn't learn about by searching online. So I'm just going to tell you up front, if you ask me any question about Intel product at all, I'm just as likely to lie about it as tell you the truth. So just don't trust anything I say about any Intel product, and we'll be fine. All right, so here's what we're going to do today. Oh, gosh, I didn't know I had all these builds in here. We're going to talk a little bit about the history of OpenMP and just a high-level overview. I want to help build a conceptual framework for you so you can walk out of here and deeply grok OpenMP. Though obviously in a 1-hour lecture, I'm not going to cover every single topic in it. That's okay. As long as you have a solid understanding of the big picture and how to work with OpenMP, I will consider this a success. Then we're going to introduce the key elements of OpenMP, and I'm very much going to shift to a style of presentation where I'm talking programmer to programmer. It's going to all be about code. Some of you will hate it. Some of you will love it. Hopefully more love it than hate it. If you hate it, just go ahead and take a nap. I will not be offended. Then we will walk through just some of the key features in OpenMP 2.5. And I'll talk about the memory model, something I'm really into with OpenMP, and the fact that you should never use a flush. And then we'll talk about OpenMP 3.0. And then if there's time, there almost never is, but if there is, we'll talk about what I call the NUMA crisis and OpenMP. So does that sound reasonable? Is this kind of what people were expecting to get in this lecture? Head nods? Okay, good, good. All right, so let's go ahead and get started. OpenMP overview. So OpenMP is an application programming interface for writing multi-threaded applications. The bulk of what you'll find in OpenMP is a set of compiler directives and library routines, a small number, for parallel application programmers. So I would never write a parallel runtime system in OpenMP. If you're going to do something like that, you use pthreads. You use something that gets you really close to the hardware. This is all about you physicists and, at the top of the heap, chemists out there who want to get their application software running in parallel. The goal was to make it for the Fortran, C, and C++ programmer as easy as we think we could make it. I actually get a real kick out of it when people tell me that OpenMP is really low level. It's like, come on, low level? It doesn't get much higher than putting a pragma in front of a loop and have it running in parallel. So we couldn't figure out how to make it any easier than OpenMP. Maybe we lack imagination, I guess. And another thing about OpenMP, and I think this is true of any good standard, is we very deliberately set out to standardize existing practice. I like to point out that OpenMP, which is probably the most important, definitely in terms of impact, probably the most impactful work I've done, it's also the most boring. Because all we did is we looked at 20 years back in time and just standardized what people were doing anyway. But that's important for a standard. You know, standard is not the place to try and invent something brand new. That's what happened to MPI 2.0, where they invented this new spec in 1996, and it was 2001 before you could have any general purpose implementation of it. That's because they standardized a research agenda, which is a huge mistake. So at any rate, let's dig into it. Everything comes from somewhere, and I think it's useful, at least for a moment, to think about the prehistory of OpenMP. So in the late 80s, I assume we're all old enough we remember the late 80s real clearly, right? I guess some of the grad students these days aren't. Wow, makes me feel old. At any rate, there were a number of attempts to standardize parallel Fortran. In the late 80s, if you did serious computing, it was all in Fortran, for performance at least. And so there are these two efforts, PCF, Parallel Computing Forum, and then there's even an ANSI standard, X3H5, in the late 80s. And they all came together and worked really, really hard to create a standard. And it didn't take off at all. Because what happened was the vendors, the big bad vendors, you know, the people from companies like Intel and IBM and SGI and DEC, yes, DEC, some of you may remember DEC, DEC. We all realized that proprietary APIs was a competitive feature, because if you bought my machine, it only ran my API for shared memory. You had no choice but to buy future machines from me. This was good. Why would I want to standardize? That's nuts. And even supposedly portable tools, like this wonderful tool CAP from a company called Cook & Associates, even that they couldn't really make portable. They had to specialize it for each platform. What happened, and there's a reason I'm walking through this, what happened was the following. We got to a point in history. Let me get rid of the stupid builds on this. All right. We got to a point in history where an important customer, the ASCII program, so in the early 90s, the Accelerated Strategic Computing Initiative, mid-90s, sorry, was basically the standard feeding trough for high-performance computing. If you did supercomputing in the United States, you wanted to get money out of this program, both in terms of buying hardware and funding software research. And the software group at the ASCII program was led then by Mary Zolzal, who's a hero of mine. She's one of, I think, one of the most heroic figures in computing. And she basically was pissed off and sick and tired of every time they bought a new SMP machine, they had to recode all their software. Even though the algorithms were the same, even though the underlying machine model was the same, if you bought one from SGI or IBM or, heaven forbid, Intel, who was selling pretty good SMP hardware at that time, you had to recode because everyone had these proprietary sets. And she had the vision to realize that as a user in a program that was steering money, she had a lot of power. And she used that power. She used that power to say, if you want to sell machines into the ASCII program, you will participate in creating a standard. And every single one of us stepped in line. Now, fortunately at that time, there were people with real strong motivations. So Cook & Associates, a little small software vendor, needed a big market to survive. SGI and Cray merged right about that time, which means they had these two different directive sets that had to come together. So this cast of characters came together. They created a straw man API and then invited a bunch of us to join in and create a standard, which is when I got involved at Intel. But IBM, HP, and yes, this is old enough, that's not a typo, that's DEC. It was Compaq later on, but at that point it was still DEC. And we came together and created OpenMP. Now the reason I go through this is, well, first off, I love history. And I think we in the technology field do not spend enough time thinking about history. But I just want to repeat, when you all speak with one voice, when you all come together, remember, we vendors only make our money if you buy stuff from us. And if you all stand up and say, we won't buy stuff from you if you don't standardize around this, then you will save us from our own bad habits, because our bad habits will lead us into proprietary APIs. So remember that. You have power, please use it. So that's the history of how OpenMP was born. 1997 1.0 came out, took us a year to come out with the C++ version of that. In doing that, we found all the things we did wrong in the Fortran version, so it took us a year to come out with the Fortran version. And you can see it kind of bounced back and forth between Fortran and C, C++. In 2005, we created OpenMP 2.5, which is actually a beautiful piece of work. Basically, we got some good computer scientists. As much as I bash computer scientists, a lot of this work was by people like me who don't really know a lot of computer science. But with 2.5, we got some really good computer scientists to come in there and get us to clean up the language, and it's a much higher quality spec. Then a few years later, we came out with OpenMP 3.0. We're currently working on OpenMP 3.1. It should be complete by the end of this year. All right, last thing I'm going to say about all these boring numbers and version numbers, why do they matter? Most everybody, GCC, Intel, IBM, are at OpenMP 3.0 today. Microsoft, which has a very nice implementation of OpenMP, they're just at OpenMP 2.5. Remember when I told you about customer power? Please, push on Microsoft. They're wonderful people. I love Microsoft. But they need to update to 3.0. And they won't do that if their customers don't insist on it. So there we go. Let's talk about the basic execution model of OpenMP. So we call it the fork-join model. The idea is your program starts out as a single thread. You get to some point in the program where you could use additional threads. You create a team of threads. Then when that team of threads is done, you fork off the threads. They work together. They finish their work. When they're done, they join back together. And you get back to this point here where you have a single thread. Then at a later point, you need another team of threads. You fork off a team of threads. Off you go. They finish their work. They join back together again. So you have a collection of parallel regions, and you have a collection of sequential parts in between the parallel regions. And the language is defined so you could have nested parallelism. So you can see over there that one thread in the team said, hey, I could use even more threads. And it created more threads. Unfortunately, most of the people implementing OpenMP don't value nested parallelism. So I'm just going to be a little, really painfully honest with you. Nested parallelism usually doesn't give you much performance benefit because of the run times that OpenMP uses, which is a shame. Because there's nothing in the model that says it can't be great. All right, so the essence of OpenMP. So for those of you who've just been dying to take a nap, you can start after this slide. So the essence of OpenMP is you're going to create threads that execute in a shared address space. OpenMP is all about threads in a cache-coherent shared address space. The only way to create threads is with a construct called parallel. It's a parallel directive. And once created, all those threads will execute the code inside the construct. Now, because you have a share, And then you split up the work between the threads. And people in practice use an SPMD pattern. I'll mention a little bit about patterns in a moment. Or they use these work-sharing constructs. So you create the threads with parallel. You split up the work between the threads, either in the code with SPMD or a directive. It's a work-sharing construct. And then the real work of OpenMP is managing the data environment. Because you have to make sure, I assume the last talk talked about race conditions. Did he? He did? Good, good. Race conditions are the bane of this style of programming. And what you spend most of your time with in OpenMP programming, or actually any shared address space programming, is this last one, managing the data environment. And so we have synchronization, so you can have safe updates to shared variables, but we also have a collection of constructs that let you control when data is shared and when it's private. So that's the essence of OpenMP at a high level. Any questions at a high level before I move on? About the history, about the high-level view of OpenMP? Anything? Okay, all right. Am I boring people? Show of hands. Is this going too slow and boring? Don't be shy. Okay, good. So that means everyone's excited, and this is really great. Okay, good. So now, oh gosh, we're going to do this build every time? I got to tell you guys what happened. I got on an airplane to come down here. I wasn't going to say this because it's really embarrassing. And I get up to the security line to get on the airplane and open up my backpack to pull out my laptop. Do you know I forgot my laptop? It's just, I can't believe it. I left home and forgot my laptop. So these presentation slides, I had to call up Jim Demmel, and I was just like desperate. Do you have my talk from last time I gave it? Fortunately, he did. That's why there's all these builds and things, though, that I don't remember because it was 2009 when I used these slides last. At any rate, what we're going to do is we're going to walk through software development with OpenMP using this simple example. And the reason I'm doing this is I don't just want to tell you about OpenMP, because a good fraction of you may never choose to write an OpenMP program. But what I want to talk about, I want to also communicate a development and a philosophy of parallel programming. How do you actually roll up your sleeves and systematically develop a parallel program? And to me, that's almost as important as teaching you about OpenMP. And this is why much of my work is focused on design patterns. And Kurt Koitzer tomorrow morning is going to talk to you extensively about our work with design patterns. A design pattern is a commonly recurring solution to a commonly recurring problem. It's a solution-problem pair. And if you understand the design pattern, then you can move it from language to language to language. You implement the pattern, you don't really care what language it's in. Is it MPI, OpenMP, TBB, Silk? I don't care. I'm implementing the SPMD pattern. And the language is just a notation for implementing the pattern. So from a teaching point of view, and from a point of view of becoming an expert in this field, it's the patterns you care about and the associated methodologies. So that's what we're going to highlight as we go through and talk about OpenMP. So the example we're going to use, this is sometimes referred to as the hello world of parallel programming, because it's a numerical integration of that integral up there. The integrand is 4 over 1 plus x squared from 0 to 1. And ideally, well, by definition, mathematically, that's equal to pi. So if I replace it with that sum, so I have these rectangles here, when I add them all up, they should be approximately equal to pi. So it's a simple program that I can fit on a PowerPoint slide, that I can test when I get the right answer, and it actually, if you have an insane number of steps, number of rectangles, you can actually see parallels speed up. And this is what the program looks like sequentially. I assume everyone here can read C, right? Okay? Even if you're a Java programmer, which if you are, my condolences. How anyone wanting to do serious computation could use Java is beyond me. But even if you're a Java programmer, you can kind of squint a little bit and imagine this is a code you can understand. And I've tried to make it as simple as I can, that you could just cut and paste this and compile it and run it. So we compute our steps for a fixed number of step sizes. I then initialize my x. Then I have this loop over the steps, summing up into integrand, multiplied by the step size, and that gives me pi. Any questions about the serial program? Don't be shy, because we're going to use it and launch from here. So if you're confused here, we get nowhere. All right, good. Gosh, you are a smart group. I guess that's why you're here at Berkeley. All right, so how to write a parallel program. I submit that in general, an expert in parallel programming always does the following. They first start by identifying the concurrent tasks in a problem. I like to call this the wetware step. It's where you just sit and think. No tool can, well, there's many tools that try to help you. I think you'll be learning about one later today. But fundamentally, it's you sit and think. What's the problem doing? What are the concurrent tasks? Then what you do is you dive into the source code and you think about how can I organize the source code to expose those concurrent tasks. It's one thing to say that the following things can happen concurrently. It's another thing to actually have the code structured so they indeed can execute concurrently. Then you go through and you express the concurrency. You actually use constructs in a parallel programming language or API so that you actually say, how's it going to run concurrently? Then you execute the concurrency in tune. So these 4 steps are what experts do when they do parallel programming. And we're going to walk through them and teach you the key elements of OpenMP as we go through these. So here we go. Where is the concurrency? Well, pretty easy, right? The iterations of this loop, in principle, could happen independently. All right? Yes, there's a number of race conditions. There's things I'm going to have to do. But in principle, each of these iterations of this loop could be done at the same time. All right? So what I need to do is I need to expose the concurrency. So here's the first part of that. The first thing I do is I stare at this and I think about what data needs to be shared that everyone's going to use, and what data needs to be local to whoever's going to do the computing. So I recognize that everyone's going to need to have their own loop index. Each thread needs its own loop index. And each thread needs to keep its value of x independent. All right? Another thing you'll notice is that loop is originally defined, oh dear, page up, page down. Notice as I originally defined it, I initialize x and I increment by step. That's the right thing you would do for a sequential loop, right? But that's a loop carried dependence on x. So what I do is I change how I express x so I compute it off the loop index. All right? Then I recognize that this sum is a reduction. Reductions happen all the time. I'm accumulating into a single variable. So I'm going to have to do some stuff to deal with the reduction. Okay? So this is step 1 in exposing the concurrency. Any questions before I go on? None? I didn't think so. Okay. Here's the next step. This is a really common trick. We do it all the time in parallel programming, especially in NPI. Is there going to be NPI taught in this session, the next 2 days? I don't know if there is. How many people here write MPI code? That's what I thought. How many people want to write MPI code? Tomorrow at 11:15. That's good. That's good. Because as you all know, MPI, that's the language God used. So, when you go back all the way, it's MPI. So, yes.
Also, everybody who attends the hands-on session will have the option to try to write MPI code. So
good. Yeah. So, sort of the standard model of high-performance computing today is MPI between nodes, OpenMP on a node. So, if you go to any of the main National Labs supercomputing centers, you'll be surrounded by people who do OpenMP and MPI. And there's a lot of debate on what will replace OpenMP, because some architectures aren't necessarily great for OpenMP. But there's very little serious debate except at the exascale level on getting rid of MPI. So if you want to do serious scalable computing, you will do MPI. At any rate, even in MPI we do this, but here's a trick we use. So I need to somehow let each thread accumulate into its own safe region. But that region needs to be visible later on so I can complete the reduction and put the partial sums together. So what I'm going to do is I'm going to define num4 as the maximum number of threads I could ask for. All right, so I'm going to hardline that into the code. Now I promote the scalar to an array. Very common trick in the SPMD pattern. I promote the scalar to an array and initialize that array to 0. All right, so now I'm going to refer to an ID of 0. Since I'm still serial code, I'm going to fix the ID at 0. But notice where I used to have a scalar that I was summing into, I'm now summing into that array element. So now each thread has its own piece of that array to sum into. Then after this loop is done, I can do the accumulation of the partial sums. So that's the second part. Notice, though, that I've exposed the concurrency, but at this point it's still a serial program. Right? All right. Now, let's put some concurrency in here, and at this point we're going to talk about OpenMP. So in OpenMP, the top of every OpenMP program, you have to expose the few runtime library routines we use. That's in pound include OpenMP.h, OMP.h. Then I have my pragma. Now, I know there are a lot of people out there who cringe at pragmas, but this is an important style of programming, because if your compiler doesn't understand a pragma, it just skips. So if I'm very disciplined in what I can do, I can create an OpenMP program that runs just fine with a compiler that doesn't know OpenMP. That's the value proposition to pragmas. And so here's a pragma. They always start pragma OMP. Another question. How many of you are Fortran programmers? Don't be shy. All right, good. All right. Let me just say this once. I teach this with C, but there's a direct one-to-one correspondent to God's language. Yes, God used MPI in Fortran 77. We know that. In the beginning was MPI in Fortran 77, and it was good. And since then, everything's been perturbed and downhill. But in Fortran, it's going to be whatever your sentinel is for a comment, C, the $sign, then the letters OMP. So since you don't have pragma as a keyword in Fortran, you have to indicate your directives as decorated comments. So if you just replace pound pragma OMP with C $OMP, and then pretty much the same for this, you'll have Fortran. So that's all there is to it. We very carefully designed it so you can move back and forth between C, Fortran, and C++. So at any rate, pragma OMP tells the compiler this is an OpenMP pragma. Parallel creates a number of threads. And num_threads, num_threads, is how many threads I am asking for. So in this case, I'm saying, hey, system, give me 4 threads, please. That's what that num threads is. All right? Now, each thread will redundantly execute the statements between this bracket and this bracket. So each and every thread will execute all these statements. I distinguish between them. I split up work between the threads by using the ID of a thread. ID equals OMP get thread num. This is the SPMD pattern. It is by far the most commonly used pattern in the history of parallel programming. Modern languages today are deviating and exploring a richer set of patterns. But if you were to go back and look at the last 25 years of parallel programming research, you would find most of it's done around SPMD. Because it's very simple. I just have one set of statements, and they only vary by what this ID is. In this case, I use the ID to split up the loop iterations. And this is another very, very common trick. I mean, this is the whole thing about pattern programming. Because this is the SPMD pattern. If I then send you off to the lab and say, by the way, use all this, but do it in MPI. Conceptually, you're doing nothing different in MPI. You just don't have a pragma. You just have different constructs to deal with MPI, but not in terms of the parallel algorithm. So what this is doing is this is splitting up my loop iterations round robin. Thread 0 will do iteration 0. Then because I'm incrementing by num, it'll then do iteration 4, then iteration 8, then iteration 12. Thread 1 will do iteration 1, then iteration 5, then iteration 9. Thread 2 will do, you get the idea. And since each thread is storing into its own copy of sum, there are no race conditions in this program. It will work. All right? Any questions? Yes?
On the number of threads to be 4. Why not 8?
Why did I choose the number of threads to be 4 is the question. You know what? I just picked a number out of the air. Actually, in a serious OpenMP program, you import the number of threads from an environment variable. But I just picked the number to be 4. Typically, if you're going to do an SPMD pattern in a program like this where it's going to be running in isolation on a system, the number of threads will be equal to the number of processors. Not the number of virtual processors, by the way. If I have, so like on my laptop here, I have a dual-core laptop. I don't think it has hyperthreading turned on. If it did, it doesn't matter, because with this kind of program, you want the actual number of cores. So in this case, I would pick 2 for the number of cores. But if I was on a machine with 32 cores, I'd pick 32. All right. So if I ran this program, let me go back up.
Tim?
Oh, wait a minute. Oh, no, there's a different thing here. Yes?
Tim? One question from the internet regarding to an earlier comment about OpenMP and MPI. How does OpenMP compare to TBB?
How does OpenMP compare to TBB? So TBB and OpenMP are very, very different. TBB is basically a style of parallel programming that is tightly wedded to the templatized style of generic programming in C++. So if you are deeply involved with that style of programming, if you look at a problem and what you do is create generic templates that you instantiate for a particular data type, and you want to think in terms of parallel container classes, so you want to have the parallelism as part of the structure of your object-oriented hierarchy, TBB is for you. OpenMP takes a much more nuts and bolts approach to it. But TBB is either the greatest thing around or useless. If you're not into that style of C++ programming, TBB looks incredibly obtuse and complicated. But if you really like that C++ style where it's all container classes, it's basically imagine the standard template library, taken to a parallel level. If that's the way you like to program, then TBB is awesome. And this is an important point, so I'm glad this question came up. Nobody is stupid enough. Okay, some people are. Only a fool, there we go, that's better. Only a fool would try and pretend that there will be one language that conquers them all. It'll always be the case there's a collection of languages. And I think that's good as long as the number stays small. We can get out of control if we have dozens and dozens of languages. But I think it'd be nice if we had half a dozen languages to hit each major community of programmer that ran really well together. And so TBB is one of those. All right, here's a problem. Yeah, okay. Yeah. Sometimes I ask people if they can see what's wrong with this program. Why don't I do it? Can someone see what's wrong with this program? There's a bug in here. Yes?
All the elements of the summary are going to be the same hash
Well, we're going to get to that. But yes, we're going to get to that. That's one problem. And it's called false sharing. We'll talk about that in a moment. But there's an actual, that's not a correctness problem. That's a performance bug. There's an actual correctness problem with this program that I snuck in. Nope, numsteps is properly shared unless I have a bug in my PowerPoint version of this. Yeah, numsteps, it's up there, so it's going to be fine. Everyone's going to see 100,000. All right, here's the problem. In OpenMP, and I snuck this in as a slight comment, when you put the num threads clause, you are requesting a number of threads. There is nothing that says you have to get that number of threads. Okay, this is one thing that catches a lot of beginning OpenMP programmers. That you assume if you ask for 4 threads, the system will give you 4 threads. The fact of the matter is, it almost always will give you the number of threads. But some people use OpenMP in large resources that are shared between many users. So if you have a 512-node shared memory machine, and you ask for 512 nodes, the scheduler may come back and say, I'm sorry, you're only allowed a maximum of 16 nodes. So therefore, you ask for 512, it'll only give you 16. Now, OpenMP can silently give you a different number of threads than you asked for. And because I am incrementing my loop by I plus equals num, I have hardwired into my code that I got the number of threads I asked for. So this is a real subtle point, but I think it's an important one to appreciate with OpenMP. So the correct program, I have to, inside my pragma here, I say int n threads equals OMP get num threads. So I'm saying, hey, tell me how many threads you actually really gave me. And so now I increment the loop by that n threads. This version of the program is correct. And its performance would be terrible. How terrible? That's what I've been doing out there since I lost my laptop. Normally I can run it on my old laptop and I have all the numbers. I had to write all this code today. All right. When I run this program sequentially on one thread, when I run this with one thread, it takes 18.69 seconds for 999,999,999 steps. You got to go a lot of steps. All right? When I add 2 threads, it runs at a blazingly fast 17.92 seconds. And the reason is the comment the gentleman over there made. Okay, some ID, indeed, there is no race condition here. Each and every thread has its own little piece of memory to read and write into. The problem is those all have to be sitting on the same cache line. So what's going to happen when one thread wants to read and write it? It's going to go and it's going to be a cache miss. Oh yeah, because the other guy's got it because he just wrote into it. All right, I'm going to go and grab it. Now I have the fresh copy. Meanwhile, the other thread's ready to write into it. And it gets a cache miss. It says, oh yeah, come on, can you give me this one? So the performance just falls apart because I have false sharing. And this is another one of those subtleties. You know, we often like to talk about how easy it is to write software when you have cache coherent shared memory. And I think a lot of what we call so easy is actually an illusion when you actually talk about optimizing and really working with the code, because there are lots of these gotchas that sneak up and bite you in the butt. So how am I going to fix that? I got to get it so that I'm no longer writing into this array. Because it's in the middle of a tight loop, that's going to get me into trouble. And so here's how I get rid of the false sharing. Oh dear, I don't talk about it yet. Let's get rid of the false sharing first. Oh, man. Here we go. Let's get rid of the false sharing first. So here's what I do. I create a variable psum equals 0. So now because I create it in this block of statements, it's created private to each thread. Each thread has its own copy. So now I'm doing the sum into each thread's own copy. And chances are it's not going to sit on the same cache line. Then, but I still have to combine the partial sums, right? I have to combine the partial sums when I'm all done. So I have sum plus equals psum. But if that happens while one thread is trying, if the threads clobber each other, one thread's updating its copy. Meanwhile, before it's done, another thread tries to update its copy. That's a race condition. So pragma OMP critical creates a critical section. And a critical section defines a block of code that only one thread at a time can execute. So if a thread's coming along and it hits the critical section and someone else is in here, it will pause and wait at that critical section until it's done. So this version of the program is perfectly safe, it works correctly, does not have false sharing, and it runs in 5.93 seconds. Big performance difference. We went from 18 seconds to 6 seconds, just by that one little change. There's extra synchronization overhead because of this critical section, but that doesn't matter compared to all those cache misses. So false sharing is a very important thing. And when I do the hands-on version of this course, I don't talk about false sharing. I let students discover it. So for those of you who teach out there, it's a great exercise. You just give them this program, they do the SPMD, and they're like, why does my performance suck so bad? And it gives you a wonderful way to bring false sharing into the discussion. So what I want to emphasize, and this is something we make a real big deal of in OpenMP, is we try and encourage you to think of parallelism as an incremental process. Because notice I went through a series of stages. And at each stage, I did a behavior-preserving transformation of the code. What that means is I can build a test suite. I make a transformation, I test. I make a transformation, I test. So at every given point, I have a working program that I can validate. Believe me, when you take shortcuts to not do this is when you get in trouble. So I make behavior-preserving transformations that I can test at each time. I make my concurrency incrementally by adding these directives, but I do it stage by stage by stage so I can test the results. And then I go through and I continue this as I optimize, as I do things like change that array to put in the critical section. But you view the programming process, the parallel programming process, as a sequence of behavior-preserving transformations so you can always test after each change. If you do that, you can maintain your sanity as you write parallel software. All right? Yes?
Do you recommend writing a sequential program first and then going to the OMP version?
So do I suggest writing a sequential version first, then going to the OpenMP programming? Wonderful question. Yes, for OpenMP, we wrote OpenMP thinking you would be starting from a sequential program. And so you write the sequential program first, you debug it, you validate it, then you transform it step by step. That's the methodology we suggest with OpenMP. Now, since some of you are going to do an MPI, and whether you all know it or not, most of you are going to write MPI eventually, whether you want to or not. One of the problems with MPI is you can't do this. Because MPI, you have to go through and you have to tear your data structures apart because you don't have shared address space. You have to decide this data will go with that process, this data will go with that process. So it's really hard, not impossible, but it's really hard to do this incremental approach with just MPI alone. And therefore, most people don't. And that means the work up front with MPI can be a lot more. But it's worth it, because MPI is just wonderful. Oh, truly wonderful. I love it. Now, this is all kind of a pain in the ass. Remember I told you that OpenMP, our goal was to make it as easy as possible. Clearly, we can make it easier than this. And we can. So remember I told you that with OpenMP, you always create threads with a parallel. If you don't see Pragma OMP parallel, you don't have multiple threads. And then we're using the SPMD pattern. The SPMD pattern says everyone runs the same code. It's single program, multiple data. Everyone runs the same code, but they have their own data. And we select it through this ID and knowing the number of threads. So this is the SPMD pattern. But I said there's a second way we do it, and it's using work-share constructs. Here we go. Pragma OMP parallel, that's the same you've seen before. This says create a team of threads. That for says take the following loop and split up the iterations among that team. Pragma OMP parallel for. So it's saying take this loop and split it up between threads. Now, when you do that, you have to somehow take into account, though, that you need to control what's shared and what's not shared. Remember, we did that before with this kludgy by creating the parallel region and then declaring data inside. I'm not getting rid of that. So what am I going to do? I add this clause called private. What private says is create a team of threads and give each one of them their own copy of this variable. So I've declared I and X out here, But each thread is going to be created, and it's going to be given its own copy of I and its own copy of X. All right? As a little subtlety, for pedagogical reasons, I put that I there. OpenMP says that the loop control index for the parallel loop, it'll make the loop control index private by default. So I could have left that I off. My style of writing, I always put it in there, just because I'm kind of lame and I like to remind myself. All right, then remember that reduction, where we create a copy of a variable to hold the partial sum in each thread and then put it back together. Okay, we have a reduction clause. We define the operator the reduction is over, which is plus. Then I define the variable. And what that says is each thread in the team will create its own copy of sum. We will initialize it with the identity for that operator, 0 for addition, 1 for multiplication. It's the obvious one. And then it's going to go through and do the accumulation into the local variable. And then when it's done, it will intelligently put everything back together again. All right? To give you a single sum. And then it will add it with the global value. So this right here is a working version of the program. And that running on my fancy new laptop, which I had to buy because I forgot my own. That's the punishment I get for forgetting my laptop. Ran in 4.59 seconds. So the SPMD version without false sharing ran in 5.93 seconds. This version ran in 4.59 seconds. So it ran even better. But what's important here is what's the difference between this and the sequential program we started with? I added the include OMP. I added a single pragma. That's the only change I made. And that's a very important goal we had in creating OpenMP. We were trying to go after a style of programming where you just sprinkled pragmas throughout your program and you picked up parallelism. That was the goal we were shooting for. And it's pretty darn simple in that regard. There's a lot we can criticize with OpenMP, and I'll actually get to some of that. But you know, it's pretty nice that you just put some pragmas and you get some parallelism. I think you were first.
I have a question. I think there's a small problem between sequential and this version of this parallel program. The results you will get with this will not be the same as the ones that you get sequentially because you have a roundup there.
That's right. Absolutely right. You think that's a problem?
Well, I think, for the repeatability of results. I mean, the sequential
You know, I couldn't have staged that question better. So a lot of my career has been spent as a numerical analyst.
Repeat the question.
I will. A lot of my career has been spent as a numerical analyst. And, you know, you get kind of arrogant. I'll admit it. You know, you get kind of arrogant when you're a numerical analyst because most people don't understand numerical analysis. They don't understand round-off errors. They don't understand this stuff. And they blithely plunge ahead, ignoring all these issues. And then we numerical analysts come in and save their asses when they make horrible mistakes and become the heroes. So the question was, touching on a pet peeve in numerical analysts, the question was that the result from this loop is not going to be identical necessarily to the sequential loop. And the reason is that floating point arithmetic, while it is associative, you're not guaranteed of getting the same results because of round-off error. And if I change floating point arithmetic is not associative. Therefore, I'm not going to get necessarily the exact same result. So the sequential program, the orders of the sums are potentially different than the parallel program. And that is absolutely correct. And I remember having people who I thought were intelligent tell me that that's because OpenMP was broken, that it should assure that you go in the serial order. But here's my response, and now I'm talking as a numerical analyst. There is no single order mathematically defined in the summation that is correct. Therefore, every single order is equally correct. So the results may not be the same, but if the variation between single thread and multi-thread matters to you, your problem is you have a bad algorithm. Because a stable algorithm has to give you answers that any mathematically allowed interleaving of these operations is correct. So yes, you are absolutely right. And for debugging purposes, it can be nice to have bitwise consistency. I'll give you that. But in terms of numbers you can work with, if the variation due to your reductions changing the associativity of the addition operations, if that matters, then your algorithm is broken. And you have to go back and rethink how you formulate the problem. Because every way I can interleave these is equally correct. And to pick one artificially, and I can't tell you how many people do this, They pick one artificially and say, well, that's the right order. The sequential order is correct. It's like, well, why? Every order is correct. And so it's subtle, but a very important point if you're going to actually do anything with these numbers. And I've had many arguments with people over this, but they're wrong because they don't understand numerical analysis. So did that answer your question? And you understand numerical analysis. I know that's exactly why you asked it. You're one of the smart ones, I'm sure. Yeah. I just, was using your question to point that out. Yes?
How did this program pick up the number of threads that you can
Good question. Yeah. Okay. Thank you. So this is actually how you would write this program in practice. Because you don't want to hard code the number of threads into your source code. You want someone, when they run it, to say how many threads they run it on. So each thread has something called an internal control variable, and or ICV for short. The internal control variables define the properties of the runtime system as the OpenMP program runs. And there's an internal control variable with the master thread and with all of the threads. One of the internal control variables is the number of threads to use. And so if I don't ask for a number, it uses the default, which is sometimes the number of processors. So in practice, what you do is you write the code this way, and then you set an environment variable. And the OpenMP spec defines a set of number of standard environment variables. I would set an environment variable, which would set that internal control variable. So this way, I compile the program once, and then I can say, run it with one thread, run it with two threads, run it with four threads. Because when you're studying OpenMP, that's the sort of thing you want to do. So that's what I would do, is I pick that up from the environment. Okay, any other questions before we go on? I have to keep an eye on time because we're running out. Okay, so there's the reduction, there's the private clause. All right, so now let me talk about the rest of OpenMP 2.5. So there are some very common recurring synchronization constructs that a shared memory programmer uses all the time. I've introduced one of them to you already. It's a critical section. It defines a block of code that only one thread at a time can execute. Okay, that's perhaps one of the most common. The only thing that may be more common is a barrier. So a barrier says all the threads will wait here until every thread has arrived here. So if I have 100 threads, the first threads to get here will wait until the full set of 100 threads arrive. Then you move on. So a barrier is a very important synchronization construct. And if we had a really long version of this, I give tutorials of every length with OpenMP, we would walk through this in a lot of detail because there's actually reasons you would write code just like this. But anyway, I initialize some data. This is an SPMD pattern. I initialize some data. I'm going to use this array A, so I don't want to go on until everyone's finished their initialization. So I put a barrier. Now I come into a loop. I'm going to do this loop in parallel, and I don't want to go on until everyone finishes. So fortunately, at the end of a parallel loop, OpenMP puts a barrier for you there by default. Remember, OpenMP is to make application programming as easy as we can. So we make it so that the default behavior is the safe behavior. The safe thing is when you do a parallel loop, you don't go on until everyone finishes that parallel loop. That's the safe behavior. As you can imagine, though, a barrier is a pretty expensive thing to do. If your goal is to get lots of stuff happening at once, you want to minimize the number of barriers. They just clobber your performance. So, for example, if you read the fine print, and these slides will all be available to you, in this case, I very carefully picked the data. So this following loop, you don't need to wait until it's done. There's nothing that's following it that uses what's in that loop. So I can say, do not give me that barrier by putting a no-wait clause. So if I put a no-wait clause on a parallel loop, I'm saying, don't do that barrier, please. Okay? So that's it for that. The other thing, we have a construct, and this is very important for you people who are mixing OpenMP and MPI. This is called the master construct. Now, earlier on when I showed you that fork join thread, you notice one was in red. That's the master of the team. And it's always thread ID 0. So what this says is, I'm creating a bunch of threads, they're doing a bunch of stuff, and then I have one thread only called the master thread, and it does something else. Everyone else keeps right on going. So I put a barrier there to make them wait until the master is done. Then the master gets there, and then they all go on and do something else. So if I were putting MPI calls, mixing it, so it's doing a hybrid MPI OpenMP program, I want to make sure, because of the properties of MPI, the safest thing to do is to have only one thread interact with the MPI. So here I have the master thread. I'd put all my MPI code inside here. That's just one style. There's a whole other talk about mixing MPI and OpenMP, but this is the safest way to mix MPI and OpenMP. All right, there's a bunch of runtime library routines, and just briefly, I won't go through all this because we're almost out of time. I've already shown you get thread num. I've already shown you how to get the number of threads. This other one here is I ask for how many threads, OMP set num threads. What this does is it sets the default internal control variable for number of threads, so every subsequent parallel region will ask for that number of threads. And what I'm doing right here is I'm saying, by default, OMP set num threads, give me a number of threads equal to the number of processors. That's what that statement does. I think it's pretty straightforward, right? And you know, the beauty of it is, oh gosh, one more thing. Okay, so here's a more complicated loop that I'm going to do in parallel. And notice when I first showed you this, I had Pragma OMP parallel 4. I can split it up. Pragma OMP parallel, we can go do a bunch of stuff. Pragma OMP 4. So I can mix this style of SPMD and loop. So I can have everyone go off and do a bunch of stuff to get ready, and then they're going to share this loop. Now, this is a loop pulled out of the cutoff method molecular dynamics kernel. And the thing is, depending on the neighborhood of each particle, I could have a very different number of iterations on this inner loop. Okay? So if I just split up that loop where I give a fixed static decomposition to each and every thread, I may not get the best load balancing. So in OpenMP, we have a whole collection of things we call a schedules clause. And I can change the schedule. What I'm basically doing is I'm interacting with the runtime system to tell it how to split up loop iterations among the threads. And we don't have time to go through it in detail, but it's the kind of the obvious things. You know, do I break it up into a static number at compile time and distribute it? Do I dynamically, so here's where I basically put the threads in a work queue. And so I dynamically go through, and then there's others. So, but these are the common things. The idea is I'm interacting with the system to tell it how to split up loop between the threads. So that's really the key constructs of OpenMP. We've actually covered the bulk of it that people use in practice. Obviously, there's lots of corner cases. But you now know enough to start writing code and to pick up one of the OpenMP books and guides and self-learn from here. So remember, the only way to create threads is the Pragma OMP parallel. All threads execute the instructions in a parallel construct. So Pragma OMP parallel, bracket, bracket, everyone's going to execute those instructions. We talked about how you split work between threads. So I can use the SPMD style, where everyone runs the same code redundantly, but they use the ID to split it up. Or we have work sharing constructs. And so I showed you about the Pragma OMP 4. There's actually a few others. I can combine them. So if I'm just going to create a team of threads and then immediately create a parallel loop, I can put the Pragma OMP parallel and the Pragma OMP 4 on one line. Gosh, then we got the high-level synchronization, and it's safest. We have critical sections and barriers. And there's more to OpenMP, but as I said, this right here is the bulk of it. And this is one of the things, from pedagogically, for those of you out there who teach, I really love starting students on OpenMP. Because here, after an hour lecture, they now can go off and start writing code. Now, they're not going to be expert OpenMP programmers. There's tons of little details and gotchas and fine nuance. But you can basically start writing parallel code and start seeing speed up, start seeing race conditions. We love race conditions. Start seeing all sorts of features of a parallel program with very little overhead to get you started. So that's very nice. Now, in the 5 minutes remaining, I was going to talk about the OpenMP memory model. And you'll have these slides. I urge you to take a good look at them. I actually got in trouble at Intel a year and a half ago, big trouble, because I publicly questioned the wisdom of cache-coherent shared memory. And of course, Intel is really into cache-coherent shared memory. Well, we have it in all our products, right? So what's with this Intel researcher going around telling people that cache-coherent shared memory won't scale, you should just not depend on it, stop using it. The reason I say that is these memory models. When you start digging into the memory models of a cache coherent system, they get really complicated because cache coherence tries to give you the illusion of the serial order of sequential consistency. But the fact of the matter is that any cache coherent system out there uses a relaxed memory model. They relax from sequential consistency. And it's very easy for you, unwittingly, to write a program that exposes the difference between the relaxed memory model and the sequential consistent memory model. And debugging those kind of problems are a nightmare. In fact, you can prove, there was a paper I can't read because some mathematician far smarter than me wrote it, but in this paper they proved that if you use mutexes in a program, proving that you have not violated a rule of the memory model is NP complete. So this is the danger of cache coherent shared memory. So even though I have a lot of personal careers in stock, with OpenMP, when I sit down to write code, I tend to write it in MPI because it's safer in many regards. So I was going to walk you through the memory model and explain the flush, which is a construct we use to interact with the memory model so that you can tell it where you need to be sequentially consistent. The other thing was going to talk about oh yeah, here I give you a nice piece of code. Gosh, I didn't do these builds. I don't know how they got in here. All right. There we go. All right. OpenMP 3.0. OpenMP 3.0 was created in May of 2008, so it's old by now. And we basically cleaned up a bunch of stuff in OpenMP. That's always the case when we come out with a new version. The big thing we added was tasks. Because the thing is, in computing, splitting up loops, SPMD will only carry you so far. If you really want to look at covering every class of algorithm out there, you need something more. And here's what you need. It's called a task. So imagine I have this loop. I have a list, a node pointer to the list. I'm going to traverse the list and process each point in that list. Right? You do this in programs all the time. OpenMP cannot handle that very well. Traditional OpenMP 2.5. The reason is, if I'm going to split up this loop, I have to know, with information available to me at compile time, what are the limits on that loop, at least by a variable, so that I can figure out how I'm going to split it up and schedule it. But just walking through a list, but the compiler has no idea how to deal with that and set up code that can deal with it at runtime. So splitting up this loop just plain doesn't work. And I often, once again, when I'm teaching OpenMP, I tell students, using the constructs from OpenMP 2.5, parallelize this. And it probably takes about 75 lines of code to parallelize that 3-line program. It's ugly. All right. So knowing, though, that this is incredibly important, we needed to add something in OpenMP. It proved that OpenMP was incomplete. And here's what we added. We added the concept of a task. So a task creates a very, very lightweight unit of work that it dumps into a task queue. Then the team of threads will come through and they'll pull work off that task queue. So we call it an explicit task. And so you can see right here what I've done. This is an OpenMP 3.0 style version of that loop in parallel. So Pragma OMP, so I'm inside of a parallel region. Okay, so I didn't show it, but there's a Pragma OMP parallel out here. Then I have a Pragma OMP single. What that says is the following line, the following block will be done by only one thread. Everyone else will wait at the end. So one thread's going to go through and walk through this loop. Right? And that one thread's going to go through, and it's going to create Pragma OMP task first private P. So it's going to create a task, and each task will process that statement, the process P pointing to data. And first private means it will capture the view of that data at the time it's created, at the time the task construct is encountered, and capture that. So what this does is one thread goes through and populates a task queue, and all the other threads can come through and execute the work on that task queue. So this expands the scope of OpenMP So we can handle basically all the stuff you see if you like Silk, or if you like any of these kind of divide and conquer recursive structures to generate parallelism. All of that is enabled in OpenMP by adding this task construct. So it's a very, very important addition to OpenMP. And this is why I like to abuse my good friends at Microsoft, and they are good friends. I love what they've been doing in Visual Studio 2010. So folks, any of you who've talked to Microsoft people, don't get me in trouble. I'm not bashing them. But they need to add 3.0 because I need to do this inside Visual Studio 2010 using OpenMP. All right? So please, talk to Microsoft and let them know you need that. I am out of time. I'm 1 minute over. Oh my God, I'm 1 minute over. I apologize. So I am done. We have to go to the next speaker. And while the next speaker's coming up and replacing me, I can answer any questions. There are no questions. Oh, good, good.
So the small question goes back to the beginning of your talk. I forgot.
Yes?
When I last tried, I couldn't get nested parallel regions from XDC. Is that so? Maybe fixed with newer versions?
Many people creating the runtimes for OpenMP never believed in nested parallelism. So they never created runtimes that implemented it well. Horrible mistake. Frankly, pisses me off because I love nested parallelism, and in principle, it could work wonderfully. But most OpenMP runtimes do not support it well. So unfortunately, I'm not surprised. You know, we design good APIs, but we have no control over how people implement the runtimes to go with it. So the design of OpenMP is brilliant. Just sometimes the runtimes, not as brilliant as the design. Any other questions? Yes? Oh, the NUMA crisis. So while he's setting up, take your time. Yeah, so OpenMP, this is funny. In 1996 and 1997, when we first created it, we're sitting around going, we're going to create this. It's for SMP machines. When was the last time anyone used an SMP machine? Symmetric multiprocessing, equal time access to every address of memory. As far as I know, the last commercial machine that could be consistently called an SMP machine was the Cray 2. And that's only if you didn't use the local memory on it. That's mid to late 80s era machine. But we don't build SMPs. The second we put a cache on a microprocessor, bye-bye to all concept of SMP. And we knew that when we created OpenMP. And we said that, you know, we'll fix it someday. We'll go back and we will provide data locality primitives. We will help you map onto the fact that memory hierarchies are not flat, are not equal access in time. So here we are, 2011, last time I checked. I think that's 15 years, roughly, after we created OpenMP. And we still haven't fixed that. Now, I'm hoping in OpenMP 3.1 or maybe 4.0 we'll fix it. We're well aware of it. But the fact of the matter is, there are times you're running OpenMP and you won't get all the performance you expect. And you have to use tricks and strange patterns to trick the system into taking memory locality into account because we don't have it built into OpenMP in the first place.
Somebody mentioned that OpenMP 3.1 is already out.
Oh, is it already out? Okay, great. I mean, I know the review draft is out. I didn't know if the final official spec was released. Okay? And I'll hand that to you.